All right, 7.10, the last lecture for this semester. We're going to go ahead and dive right in on sandcastles. Benji, Chow, and Cassandra plan to enter a sandcastle building contest being sponsored by a local radio station. The winning team gets a private beach party at a local resort for all of their friends. To be selected for the competition, the team has to submit drawings of their castle and verification that the design fits within the rules. The three friends actually plan to build 3 identical castles, each one twice as big as the previous one. They hope that replicating the same design 3 times while paying attention to the tiniest little details will impress the judges with their creativity and sand sculpting skills. Benji is puzzling over a couple of questions on the application. They sound like math questions, and he wants Chow and Cassandra to be sure that he answers them correctly. So the following questions are: what's the total area of the footprint of your planned sculpture, sand sculpture, so that's the base of it, and what is the total volume of sand required to build your sand sculpture? So the friends have only designed one of the castles, and since the others will be scaled up versions of this one, each one will be twice as big. Alright, so after studying the diagram, Benji says, I calculated the area of the footprint of the smallest castle to be 2.5 square feet, so the next one will occupy 5 square feet, and the largest will occupy 10 square feet. That's a total of 17.5 square feet, well within the limits. Number 1 is, what do you think of Benji's comment? Design a couple of possible footprints for a sandcastle that will occupy 2.5 square units of area, and then scale up each design so it's twice as big, and calculate the area. What do you notice? Well, the first thing that I'm going to do is draw a little picture here, a little diagram, so that we can get a clearer picture for this. So let's just say our footprint, or our base of our sandcastle, it's going to be 1 by 2.5 feet, okay? Because I know that 1 times 2.5 is a quick, easy way to get 2.5 square units. So now, what if I double both of those sides, okay? If I make one that's twice as big. So Benji had said, well, it's going to have an area of 5 square feet, but if we double each side, we actually end up with an area of 10 square feet, right? Because we have 2 for the height or length and 5 for the width. So there's an interesting thing, first of all, that if we do double the side lengths, then we actually are getting a much larger number than twice as big as 2.5, and it's not 5 square feet. So now imagine stacking cubes on your sandcastle footprints to create a simple 3D sculpture, and then scale up each design so it's twice as big and calculate the volume. So I'm gonna look at, here we go, just pretending. Here's my first rectangle. I'm just gonna stack rectangles right on top, with a height of 1, just to keep things simple, and this one's 2.5. So that is the rectangular version of this, okay? But then if I'm looking at the cubic version, I should say. So now if I'm looking at the cubic version of the figure on the right, I know that this side is twice as long as this side, and this side is twice as long as this side, so I'm just going to set up those bases first. So here's 1, or that should be 5. Oops. So here's 5, here's 5, and this is still, the height is still just 1, right? But then I need to double in this direction too, because it was 1 here, but now we doubled that, and so it's actually going to be 1 over there. So we really get this shape that is not just, now we've got 2, oh, and I should say, that's not 5 yet, it's 2.5 and 2.5, right? So this whole length there is 5, and then this whole length over here is 2, right? But what we actually get is we've calculated that, or we have seen now that there are 4 of those same size rectangles, right? And then if we think about, okay, what about stacking up so that it's twice as big, because we're going to double in height as well. So if we stack it up for every unit to be twice as big, then we're going to get 1 more up here as well, right? So really, here, if you can kind of bear with me to try to see those shapes. Here's the other height there. So really we've gone up 2 with this height here. There's 2 with that, or excuse me, yeah, 2 with that length there, and then that whole length down there is 5. So when we're looking at the volume of this one is still just 2.5 feet cubed. But this one, if you've got each of those being 2.5 feet cubed, and then you have a total of 1, 2, 3, 4, 5, 6, 7, 8 of those little rectangular cubes, it's going to have a cubic volume of 8 times as many as that single one. So when we're doubling everything, we're not just doubling the volume or the area, we're actually going up by several different factors, right? From here to here, we went up by a factor of 4. And from here to here, when we doubled with our cubic diagram, we actually went up by a factor of 8, right? So when we're interpreting the phrase twice as big, in 1 and 2, our interpretation was maybe a little different than Benji's, right? So we didn't just double to have our footprint twice as big, right? When we doubled our side lengths, we ended up getting a footprint that was 4 times as big, right? So this didn't ever happen, and this won't happen either, right? If we double it again, we're going to end up with an even larger number. Okay, so we interpreted that slightly different than Benji did. So to avoid confusion, how would it be more appropriate for Benji and his friends to say that they are going to scale up their initial sandcastle by a factor of 2? So it would be more appropriate to say we're scaling up by a factor of 2 rather than just doubling, right? If the footprint of the sandcastle occupies 2.5 square feet, is it possible to calculate the area occupied by a sandcastle that has been enlarged by a scale factor of 2, or is it the area of the enlarged shape dependent on the shape of the original figure? So, for example, do triangles and parallelograms and pentagons all scale up in the same way? Okay. So when we're looking at this, we actually will see that if we're scaling up, we're basically doing a dilation of 2, and so everything increases by a factor of 2 times 2, or 2 by 2, because we're scaling everything up by a factor of 2. So that's the answer to number 4. And what happens to the perimeter of the footprint of your sandcastle when it's scaled up by a factor of 2? Well, the perimeter, if we're looking back at the perimeter is different than the area. So this one, the perimeter is 2.5 plus 2.5 plus 1 plus 1. So that is a perimeter of 7. And over here, we have a perimeter of 5 plus 5 plus 2 plus 2, which is actually equal to 14. And so our perimeter, when we scale up by a factor of 2, our perimeter is doubled. Okay. All right, let's move on to the next page here. So suppose your castle footprint was cut out of a piece of styrofoam that's 1 inch thick. What happens to the volume when this 3D footprint is scaled up by a factor of 2? So we kind of already talked about that a little bit, right? When we're scaling up the volume, like we looked at in number 2, when we scale up the volume as well, we're doubling this direction, and this direction, right? So if we think about that, if our original rectangle, here, let me draw one more picture, I'll try to make this one less confusing. If this is 2.5, or let's just actually even make it simpler and say, this is the length, this is the width, and we know that our height is 1. Width, there we go. Then if we're going to double this in every direction, right? Oops, that one's going height-wise. So then we'll end up with a 2 high with 2 times the length here and 2 times the width here, right? And as we know, our volume formula is just length times width times height, or length times width times height, right? And so if we're looking at the volume of this one, it would be length times width times 1. If we're looking at the volume of this one, it's going to be length times width times our height, which is actually 8 times length times width, right? So we've gone up by a factor of 8, as I had kind of talked about a little bit before. So the plans for the smallest sandcastle include a rectangular prism that's 5 inches high and has a square base with a side length of 2 inches. So that's our smallest sandcastle. Up to this point, we've just been working with hypotheticals, right? But they want us to know, or they want us to find out what's the volume of sand required to make this prism in the smallest sandcastle. So if it has a base, a square base, that's 2 by 2 and a height of 5, well, we know that our volume is just going to be the length times the width times the height. So it's 2 times 2 times 5, which is equal to 20 inches squared. Okay, so what then would be the volume of sand required to make the prism in the middle-sized sandcastle, right? So if now we're doubling every length, right? So now it'll be 4, make that a little bit longer, times 4 times 10, and this is not going to be exactly to scale because I'm just eyeballing. Okay, so 4 times 4 times 10, so now we actually will get a volume, oh, and this should be up here, not squared, that should be cubed. We'll get a volume here of 160 inches cubed, right? So we've already gone up by a pretty large factor. And then what's the volume of sand for the largest sandcastle? Well, now, and I'm not going to make my drawing any bigger, I'm just going to double the numbers, 8, 8, and 20. So now we've got 8 times 8 times 20, and that's going to be 1,280 inches cubed. Okay, so that's even larger. Okay, we're going up pretty rapidly from 20 inches cubed to 160 inches cubed, then all the way up to 1,280 inches cubed. So now, what about the perimeter of each of the squares that form the bases of each of the three prisms in each of the three sandcastles? So what's the perimeter of each of them? Well, we've got 2 and 2, so we're going to just go 2 plus 2 plus 2 plus 2, 4 plus 4 plus 4 plus 4, 8 plus 8 plus 8 plus 8. So the first one would be equal to 8. The second one would be equal to 16, and the third one is going to be equal to 32, right? So if we're looking at this, we've got 8, 16, and 32, right? So what's the total surface area of each of the rectangular prisms used in constructing each of those three sandcastles? So we need this information to then construct the nets for the molds, right? So we'll need to find the surface area of each of those. But before we do that, I want to just look at the fact that this is 8 times 2, 16 times 2, and we get our next number, right? That's an interesting thing to look at as well. So anyway, now let's move on to the surface area. So if we're thinking about surface area, we just need to find the area of each surface and then add them all together. So we have 4 surfaces that are going to be the same, right? Those 2 by 5 surfaces. And then we have 2 surfaces, the base and the top, that are going to be the same as well, 2 by 2. So we're going to have 2 times the area of the base, which were 2 by 2. So I'll do 2 times 2. And we have 4 that were the area of those side faces, which is 5 by 2. Okay, so when we multiply that out and add them all together, then we'll get the areas there. So let's do that same thing for the next 2 surface areas as well. So again, we've got 2 bases, the square bases, which are 4 by 4 in this case. And we have 4 of our side faces, which in this one, oops, not that one, this one, are 4 by 10. Okay, and then our last one will be, we have 2, the base and the roof that are 8 by 8. And we have 4 of our side faces that are 8 by 20. So when we go ahead and multiply those out, let's see. This top one, we should get 48 inches squared. Right, the next one we should get 172 inches squared. And the last one we should get 768 inches squared. All right, so interesting information. Again, we're going up more quickly than just in our linear fashion, right? Where this was times 2, and then we got our third one. This is not times 2, right? Neither was the volume. This was not times 2. That was actually times 8, right? And times 8 increase. That was the same thing to there, right? So now let's look at number 8, which I believe should be our final. All right, so now let's look at number 8. So Chow and Cassandra plan for the smallest sandcastle to include columns in the shape of cylinders with the base of the circle with a radius of 1 inch, and the height of the column is 12 inches. Okay, so we've got a circle right down here. Let me get my drawer out. So a circle with a 1 inch radius, and then the height of 12 inches. Solid sandcastle construction here. So what is the volume of sand required to make each of these columns in the smallest sandcastle? So this is the smallest sandcastle. So we need to find the volume, and the way you find the volume, and this is just a good general rule too, the way to find a volume of a figure is to take the area of the base of that figure and multiply it by the height. So we're just going to look at the area of the circle and then multiply it by the height. Okay, so we're going to have pi r squared, which is pi times 1 squared times 12. We know that 1 squared is just 1, times 12 is just 12 pi. And this again is going to be in inches cubed, right? Volume is always in a cubic unit. So now what about the volume of sand required to make this column in the middle-sized sandcastle? Well, if everything goes up by a factor of 2, we should now have this being 2 and 24. Right, so again, we're going to do pi times the radius squared, so pi times 2 squared times the height, the area of the base times the height. And now we've got 2 squared, which is 4, times 24, which should get us 96 pi inches cubed. Okay. And then the volume of sand required for the column in the largest sandcastle. Now we're going to have our base will be 4, right? So we're going to do, or our radius will be 4, and then it'll be 48. Okay, so we're going to have pi times the radius squared times 48. And when we multiply that together, we should get 768 pi inches squared, or inches cubed. Okay. So again, when we look at how we're increasing in our surface area, or in our volumes, we're increasing pretty rapidly, right? From 12 to 96 pi, from 12 pi to 96 pi to 768 pi, just by doubling the linear values of these, right? So now, what's the circumference of the circles that form the circular bases of each of the 3 different columns in the 3 different sand castles? So we need to find the circumference, which is just 2 times pi times r, or pi times the diameter rather. So we're going to have 2 times pi times 1, which is just 2 pi for that first one. The second one will have 2 times pi times 2, which is 4 pi. And the last one will be 2 times pi times 4, which is actually 8 pi. So notice this one, again, went up by a factor of 2, right? All went up by a factor of 2. So now the total surface area of the cylinders, including the 2 circular bases, and the rectangle that wraps around them to form the cylinder in each of the 3 sandcastles. So this is actually pretty interesting. When we're thinking about surface area of cylinders, we imagine those different pieces. So here are the circles for the bases, so we'll need to find the area of those. And then we've got the sides here. And this is a curved shape, right? But what we can figure out is we can actually, if we were to slice this right here and unroll that around this circle, what we would actually wind up with is a perfect rectangle, okay? And the rectangle would have the height of the cylinder, so whatever that height is, and This side right here would be the circumference of our circle, okay? So when we're finding the surface area, we just have to find the area of both of our circles, there, and then the area of this rectangle and add them together. So we know that our circles on the top and the bottom are going to have the same area, so I am just going to multiply the area of one of them by 2. So it'll be 2 times pi r squared, which is, in this case, 1 squared, right? So we'll have 2 pi for the area of the first one. And now we need to use the circumference of that first one right here, because we're going to add that together, right? So actually, I shouldn't have even written that yet. It'll be 2 pi times 1 squared plus the area of our rectangle that wraps around the cylinder, and the circumference of the circle in the first pyramid, or the first sandcastle, the circumference for that one is 2 pi, and the height is 12. Okay, so that's what we'll get there. Then we're gonna, before I do calculations, I'm gonna move on to the next one. So I'm gonna take 2 times the area of the circle bases, just because I know I have 2 of those bases, plus I'm going to take the circumference of that. So this one is 4 pi, the circumference of that circle, times the height of that prism, or the height of that cylinder, okay? And now I'm gonna do the last one, 2 times pi, because I have 2 of those bases, pi r squared, so 4 squared, plus the circumference, which is this thing, this thing right here, right? So the circumference of the largest cylinder times the height of the largest cylinder, okay? And when I multiply those all out, I should get 26 pi inches squared. I should get 104 pi inches squared. And I should get 416 pi inches squared. So when you are looking at these, you'll actually see that they go up by a factor of multiplying by 4 and by multiplying by 4. Whereas this linear one went up by a factor of multiplying by 2. And if you look back up here, this actually goes up by a factor of multiplying by 8. Okay? So when we're dealing with things in a linear fashion, just one way of increasing, right, goes up by a factor of 2. When we're looking at square surfaces, they go up by a factor of 4. And when we're looking at cubic or volumetric shapes, they go up by a factor of 8 when you have a linear increase of just 2. All right, that is all for today. Enjoy your RSG.